For this vodcast, please have no pages number 7 and number 8 in front of you. Topic of discussion today is going to kind of carry over from the last vodcast in dealing with the homologous series. We're going to focus our attention today just on the alkanes. All right, we're going to look at saturated aliphatics. We'll take a look at some straight-chained alkanes, some branch-chained alkanes, and then finally we'll get into a discussion on how to name these branched alkanes. Okay, first off, with the alkanes themselves. Many of these saturated aliphatics, they are used as burning fuels. Some examples are propane, butane, maybe from camping, you might have a butane tank, propane from a gas grill. And what happens with these fuels is that you have the release of an enormous amount of energy. All right, so when these alkanes, specifically the fuels, the propane and the butane, catch on fire, they release an enormous amount of energy. All of the alkanes, they will end in A-N-E. Right, comes from this portion right here of our term, the alkanes. They are going to be saturated, which means we're going to be looking at single bonds and single bonds only. All single bonds. They will have the maximum number of hydrogens bonded to their carbon chains. So the general formula we're going to look at is going to be CnH2n plus 2. And remember, the N represents how many carbons you have within these alkanes. Now, an example that we have here is pentane. All right, in the diagram of pentane, we see that we have 5 carbon atoms. The number 5 has the prefix of pent. If we were going to go ahead and use the formula of CnH2n plus 2, you plug in 5 for the ends, you would get a formula of C5H12. And naturally, if you went ahead and counted up all the hydrogens, you should come to a grand total of 12. All right, so there's an example of a saturated aliphatic open-chain alkane. Now, specifically with the straight-chained alkanes, no branches whatsoever. They're also referred to as N-alkanes, normal alkanes. An example would be N-hexane. Right, you'll see the example of hexane many, many times within this unit. Now, the general rule for naming straight alkanes, straight-chained alkanes, is that you're going to use the prefix off of table P to tell you how many carbon atoms you have, and then you're going to just add the suffix or the ending of A-N-E. Right, now, both of these examples here are butane. Right? An easy, simple, structured butane can look like this, where I'm numbering the location of where the 4 carbon atoms would be located. Then it's just implied that those bonds off the carbon atoms are going to be attached with hydrogens. All right. Another way to write out butane, straight-chained alkane, and I like this method a little bit better, is going with the actual structural formula. All right, I'm labeling my 4 carbons. You can see the pattern is very similar to the previous example. And in this example, you can actually see where the carbons are and where the hydrogens would be located as well. So this is a straight chain. There's no branches attached to these particular alkanes. Now, speaking of the branches, let's take a look at the next category. Branched alkanes. Branched means not a straight continuous chain like we saw up here. Organic molecule that has a smaller branch or branches coming off a larger continuous chain. How can you tell if it's branched? You can't run your finger along all the carbons in just one general sweep. You will hit some sort of dead end, And you'll have to turn around and retrace part or some of your path. That helps indicate if you're looking at a branched chain or not. Now, because of this, we must establish, this is very important, the parent chain, or it's also known as the main backbone, in order to name these molecules properly. So the first thing, find longest continuous chain within the organic molecule. All right. Here we've got 1, 2, 3, 4, 5, 6 carbon atoms. But the longest continuous chain is going to go from here to there down to the bottom. All right, that's our longest continuous chain. If you try to go from here to here to here, that's only 3 carbon atoms. All right, you can go from here to here to here. That's also 3 carbon atoms. You could also go, and I'll change the color of the pen to see this. You could go from here to here to here, and then turn right and go to here. That's a 4 carbon chain. Regardless of which direction you go in, the longest parent chain is 4 carbons. Okay. Another example. The longest parent chain here would be 1, 2, 3. This direction. Longest chain. You can also get the same length and chain if we go this way too. There's 3 carbons involved there. Another route would be this way as well. All right, so there's multiple different ways or paths that you could take to find the longest parent chain, but regardless of which one you choose, you're going to be looking at 3 carbons here. Okay, the next example, here's our longest chain here. C, 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 C. There's 4 carbons here. All right, and like we talked about, if you take a look at table P, you'll get an idea of a 4 carbon chain. All right, that's going to be the butane, or the bute again. And because we're dealing with alkanes, you're going to slap the ANE on the end there. Now, we need to go ahead and identify where the chain kind of branches off as well. And you can see our chain branches off here. All right, if we were to do a count, a sweep, and go this direction, we'd only get 3 carbons. That's not the longest parent chain. 1, 2, 3, 4 carbons is the longest parent chain. Therefore, this is going to act as a branch. Once again, if you go to table P, you will notice that we identified that a 4 carbon chain is a butane. If you have just a 1 carbon chain available, that's going to be methyl. Okay. Now, the way that we would write this, number 1, is you've got methyl butane. Right, the methyl comes from this portion here. Here's your methyl piece here. Here's your butane piece here. Okay. And what we did here is we numbered the location of where the methyl group comes off of the main longest continuous chain, which is at the 2nd position. We'll spend a lot of time talking about how to name specifically on the next page. All right, we got a warning down here. Some molecules may appear to be branched, but they actually are not. So take a look at this example. If we find the longest continuous chain, longest continuous chain, 1C to the 2nd C to the 3rd to the 4th to the 5th. Now, because we're taking all these right-handed turns, turning upwards as well, you might look at it and think that it's branched, but in actuality it is not. It's one continuous chain. So if we were to go ahead and name this, we would see that we have 1, 2, 3, 4, 5 carbons, C5, and because we're dealing with the alkanes, once again, our formula is CnH2n plus 2, and we have a total of 12 hydrogens. This is called pentane. All right, the pent comes from the number 5. Now, on the next page, let's take a look at some ways to name some branched alkanes. All right, This can be slightly tricky if you're not paying close attention, so please be very careful in making sure that you're paying attention as we run through the different rules. Okay, naming branched alkanes. Now, the first thing you want to do is still locate the longest possible carbon chain. That's your parent chain. Any carbons coming off this chain, they are your branches. You're going to number the carbons in the parent chain so that the branches fall at the lowest possible number or sum. All right, lowest possible number or sum. So that's your first rule. Now, the second rule says name the branches first. So the naming of the branches comes first in alphabetical order based on their prefix, along with the number of the carbon that they actually happen to fall on. So the prefix based on the number of carbons, right? We can find that on table P, and then we finish up with a suffix of -YL. The third step, branches are named separately unless there are two of the same. If this is the case, lump them into the same branch name with the same number locations and add the prefix. So if we've got two of them that are the same, it'd be a di, 3 would be tri, 4 would be tetra, and so on and so forth. This is depending on how many C's are in the branch. Okay, and then the fourth and final step, the parent chain is stated last in the name. The number carbons in the parent chain should agree with the prefix in the last word of the chemical name. So we've got a series of examples here, and I'd like to run through some of these. We'll probably do them all together here. All right, let's start with example number 1. All right, here's what we have. Let's go ahead and find our longest possible carbon chain. That's our first step. There it is. Whoops. I don't want that to happen. Let's try this again. Won't stay for me. All right, let's just try a marker here. All right, let's go this way. Here we go. There we go. All right, there's our longest possible chain, and we have 1, 2, 3, 4, 5, 6, 7 carbons. Okay, we have one branch. All right, here's the branch that we have present within this particular organic compound. All right, we're going to make sure we go with the lowest number located where the branch is. So we can number one of two ways. We can go 1, 2, 3, 4, 5, 6, 7, or we can count in the opposite direction and go 1, 2, 3, 4, 5, 6, and 7. Based on the rule, it says that you want to number the carbons the lowest possible number where the location of the branch is going to be. So we want to go with a number system that's in green because our branch falls on the second carbon. If we were to go to the red sequence, the branch would fall on the 6th carbon. Right? We want to keep it as low as possible. So the way to name this, parent chain is going to come last. Right? We know we're dealing with 7 carbons, which is heptane. Right? And get that right off of the tables, the reference tables, table P. Now the beginning part says that we need to name the branches first. Here's our first and only branch. It has 1 carbon atom in it. That's the methyl group. We need to name the location of which carbon atom it's on. That's number 2. So we've got 2. Based on the rule, we're not going to go with methane. We're going to go with methyl. Throw another dash in there. Heptane. Okay? Let's try another one. All right, we've got a long continuous carbon chain here, and they're numbered for us. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 carbons here. All right, a 9-carbon chain is called nonane. Right, going with the ANE because these are all alkanes. Now what we need to do is identify where the branches are. Here's one branch here. Here's a branch here. There's a third branch here. Okay, this branch here has 1 2 carbons in it. This branch here has just the 1 carbon. This branch here has just the 1 carbon as well. Okay. We're going to take a look at a location. All right. We can see that we have a branch at carbon 3, carbon 4, and carbon 7. Now, alphabetically, right, like it was stated up here, alphabetical order, we're going to place the branches within our name. So if you have a 2-carbon chain, right, that's an ethyl group. Right, if you have a 1-carbon chain, like we talked about already, that's a methyl group. Okay. All right. Now, going alphabetically, ethyl is going to come before methyl. Here's what we're going to do. We're going to write down the location of where the ethyl group is, 3 ethyl. Then we're going to write down the location of where the 2 methyl groups are, 4, carbon 4, comma 7. We're going to name the methyl groups, methyl. Now, something different here. We also have to identify how many methyls we have. All right, we have 2 of them, so we're going to put a dimethyl in front. Okay, let's do one more together. Do number 3 together here, and I'm going to have you guys do number 4 and number 5. Kind of cut this podcast a little bit short. All right, so here we go. Here's our chain. All right, we've got 1, 2, 3, 4, 5, 6, 7, 8 carbon locations. 8 octane. All right, we've got, it appears to be 1 CH3 here and 1 CH3 here. So if we take a look, identify the location of where the CH3s are, or the methyl groups are. We've got 3, 4. Right, so we've got 3, comma 4. And because we have 2 methyl groups, we're going to go with a dimethyl octane. Okay, let me show you something that is of great importance here. If we reversed the numbers in our longest possible chain, and we went in this direction here, which some of us may right from the beginning, we're going to notice that this is the longest way, right? It's not the shortest, it's not the least sum of carbon atoms based on where the methyl groups are located, right? So to figure out, to make certain that we've got the lowest sum of locations of where the methyl groups are, if we were to go in this direction, you would take the number 5, that's where your first methyl group is located, and the number 6, where the second methyl group is located, and add those 2 together, you would have 11 for the total sum. Now, if we were to go back and take a look at the red number pattern, you can see that we have our first methyl group located at 3 and our second methyl group located at 4, which would give us a total of 7. Like it was noted up above, you want to make certain that you have the lowest combined locations of where the methyl groups are going to be located. So that's why we go in this direction when we start to name or number our carbon atoms. Okay, what I'd like you to do is to attempt problems 4 and 5. They're a little bit more involved here, there's no doubt about that, but I'm pretty certain that you'd be able to do these problems if you take your time.